Today we are going to be examining the behavior of an inductor and a resistor in an RL circuit, whether in terms of the charging or discharging process across each electrical component. Moreover, we are going to be determining the time constant tau of an RL circuit, which is going to be the time it takes the inductor to either charge up or to discharge down to certain percentages from its maximum value. So the mathematical analysis of an RL circuit is actually quite similar to that of an RC circuit, as we are going to see in a few. We have seen before in the case of a capacitor that a capacitor is an electrical device that can store energy in the form of an electric field, whereas an inductor is also an electrical component, but that can store energy this time in the form of a magnetic field whenever you have an electrical current flowing through it. And an inductor is actually constructed by wrapping a coil of wire or a copper wire in many turns around a central core, and that central core can either be free space or it can be iron core. And we are going to see later on how the nature of that core is going to affect the behavior of that inductor, whether we have an iron core or we have a free space. Moreover, we saw in the case of the capacitor that the current flowing through a capacitor is actually a time-varying current, and in a similar manner, the electrical current flowing through the inductor is also a time-varying current. It is changing with time. However, in that case, the inductor, it has a certain characteristic which is to oppose that change in current, and that characteristic is defined as the inductance. So the inductance, which is a property of an inductor, is actually defined as the tendency of an inductor to oppose the change in the electrical current flowing through it. And mathematically, the inductance is given as n times phi b over I, where n would be the number of turns of that inductor, phi b would be the magnetic flux, I would be the electrical current applied or flowing through that inductor, and that product n times phi would be none other but the flux density which is produced by the inductor. Therefore, the inductance over here is actually a measure of the flux density that is being produced by the inductor per unit of current. Now, there is also an additional characteristic regarding the inductor, but we are going to be talking about it in a bit. First off, let's start by studying the following RL circuit, which consists of a resistor and an inductor, both in series with a battery. And over here we have an on-off switch. In a similar manner to how we have studied the RC circuit, we are going to consider over here two different time zones. A time zone at t equal to 0, which is going to be the moment right after closing the switch, and another time zone at t equal to infinity, starting at t equal to 0, right after closing the switch. So over here we have closed that switch. In that case, at t equal to 0, the current flowing through that RL circuit is yet to begin flowing. So we don't have any current yet moving through that RL circuit. So it's equal to 0 at t equal to 0. And this is because the inductor over here is going to be the limiting factor. It's going to be applying or inducing a certain electromotive force which is going to oppose the battery, and we are going to define that electromotive force in a bit. So at time t equal to 0, there is no current yet flowing through that RL circuit. Therefore, the voltage across the resistor, which is given by Ohm's law, is also equal to 0 at t equal to 0. In that case, in order for the law of conservation of energy to be applicable within that loop, therefore the voltage across the inductor should be equal to the voltage of the battery. So VL is equal to V0 at t equal to 0. So we have the maximum voltage across the inductor in that case at t equal to 0. Now switching on to t equal to infinity. So after a certain time has elapsed, now the current flowing through that RL circuit has begun to increase slowly and exponentially. And that slow increase in the current is actually due to the fact that over here that inductor, whenever it has a current flowing through it, is going to generate a magnetic flux. However, the current flowing through the inductor is actually a time-varying current. It's constantly changing over time. So in that case, that changing electrical current is going to generate over here a constantly changing magnetic flux. And according to Faraday's law of electromagnetic induction, a varying magnetic flux is going to induce an electromotive force. So the varying magnetic flux of that inductor over here is going to induce an EMF, or simply an electromotive force, which is none other but a voltage. And the polarity of the voltage of that inductor is going to oppose the polarity of the voltage of the battery. And moreover, that voltage over here is going to induce a current which is going to oppose the current of the battery. And this is why the electrical current of that RL circuit is going to increase slowly and exponentially, because it's being countered by that electromotive force that is induced by the varying magnetic flux of the inductor. So in that case, after t equal to infinity, after a long time has elapsed, the current of that RL circuit is going to be able to finally overcome the induced current of that inductor over here. And therefore, I is going to stabilize and become a constant. Once that current over here stabilizes and becomes a constant, therefore, the voltage across, or the induced electromotive force across the inductor is going to drop to zero, and therefore the induced current of that inductor is also going to drop to zero, and therefore that inductor over here would act as a short circuit. So after t equal to infinity, that current over here is going to stabilize and becomes a constant, and it's going to be equal to V0 over R, and therefore the voltage across the resistor is going to be equal to the voltage of the battery, and finally the voltage across the inductor is going to drop to zero. Now, like I said before, the aim in that part is actually to study the charging and discharging process across each electrical component. So we need to study the voltage response either across the resistor or the inductor, as well as the electrical current response in that RL circuit. How is it going to be? Is it going to be one of a charging or one of a decaying? And as we have seen over here, the only electrical component which is going to decay in that case is going to be the inductor. So for the inductor, we should expect to have a decaying expression for the voltage, whereas for the electrical current in that RL circuit and for the voltage across the resistor, we should expect to have an increasing and exponentially increasing responses. So let's establish expressions for the voltage across the resistor and the inductor, and an equation for the electrical current in that RL circuit. In order to do so, we are going to revert to KVL, Kirchhoff voltage law, and that loop over here, and we are going to choose the clockwise direction. So we are starting at the battery, moving to the resistor, moving to the inductor. So over here we have a plus V0, we are moving from negative to positive, minus VR, we are moving from positive to negative, and minus VL, we are also moving from positive to negative over here. So we have V0 minus VR minus VL equal to 0. However, VR is given by Ohm's law as I times R. So we have V0 minus I times R minus VL over here. What would be VL in that case? VL, like I said before, VL is not only the voltage across the inductor, but it's also the electromotive force which was induced whenever we had a time varying current flowing through that inductor and generating a varying magnetic flux, which in turn generated an electromotive force. We have defined previously over here the inductance to be L equal to N times phi B over I. So in that case, L times I is equal to N times phi B. But moreover, we have said also that the voltage which is generated, or the electromotive force which is generated by that or induced by that inductor, is actually induced by the varying magnetic flux. In other words, VL is proportional to the variation of the magnetic flux density over time. So over here we have a varying magnetic flux density over time, which is going to generate an electromotive force. So in other words, VL is equal to dN times phi B over dt. So that electromotive force is actually being generated by that varying magnetic flux density with respect to time. However, N times phi is equal to Li, so we can replace it by L times I. So VL is equal to d of L times I over dt. However, the inductance over here of that inductor is actually a constant. It's a property of that inductor, so we can take it out. So VL now is equal to L times di over dt, and as we can see, VL is actually proportional to the rate of change of the current with respect to time. In some textbooks, you are going to see a minus sign being added over here, and the minus sign in that case is simply for direction, to indicate that the induced electromotive force of that inductor is actually opposing the change in the electrical current. However, whenever we are finding over here the magnitude of VL, that minus sign is not going to be included. The minus sign is simply for direction. So in that case, over here we have minus L times di over dt And like I said, that minus sign over here is going to be dropped. It's simply for direction. So over here we have minus LdI over dt equal to IR minus V0. So di over dt is equal to 1 over L minus 1 over L into IR minus V0. Now we need to manipulate that equation in order to have a term which is going to refer to the time constant of an RL circuit. Noting that the time constant for an RL circuit is actually given as L over R. Therefore, that equation over here becomes di over dt minus R over L. So we have taken R out of that equation over here and we have taken it as a common factor. So minus R over L into I minus V0 over R. And then we have to do a separation of variables. So all the di variables are going to be taken to one side and all the dt variables to one side. So di over I minus V0 over R is going to be equal to minus R over L times dt. And then we integrate. Over here we are going to integrate from 0 up to a certain current, up to a certain arbitrary current I, and over here from 0 up to a certain arbitrary time t. Now over here we have, it's similar to having the x over x. The integral would be ln x. So over here the integral is going to be ln of I minus V0 over R. So ln of I minus V0 over R from 0 till I equal to minus R over L times the integral of dt would be t from 0 till t. Therefore over here the equation becomes ln of I minus V0 over R minus, now we replace the 0 over here instead of I, so we have ln of minus V0 over R equal to minus R over L times C. So ln A minus ln B, it's going to be ln of A over B. So it's ln of I minus V0 over R over minus V0 over R equal to minus R over L times C. And then we need to get rid of that ln, so we take the exponential of both terms. Therefore we are left with I minus V0 over R equal to minus V0 over R times the exponential of minus R over L times C. So that expression, we are going to continue it over here. So I is equal to V0 over R into 1 minus exponential minus R over L times C. So over here I have taken the V0 to the other side, and then we have V0 and V0 as a common factor in both terms. We have taken V0 over R into 1 minus exponential minus R over L times C. Noting that the time constant in that case is equal to L over R. So the term over here is none other but 1 over tau. And the term over here, V0 over R, is none other but I max, the maximum amount of current flowing through the RL circuit. Therefore, I of t becomes equal to I max into 1 minus t over tau. And that would be the final expression for the change in electrical current through the RL circuit. Now from the equation of the current we are going to proceed in order to determine an equation for the voltage across the resistor. So according to Ohm's law, V equal to IR, so we multiply that equation by R everywhere. So I of t times R equal to I max times R into 1 minus exponential minus t over tau. Therefore we are left with V of t equal to V0 into 1 minus exponential t over tau, and that would be an equation for the change in voltage across the resistor. Now what we are still left to do after determining an expression for the current in the RL circuit and an expression for the voltage across the resistor is actually determining an expression for the voltage across the inductor. And we have already said before that the inductor, or the voltage across the inductor, is going to be an exponentially decaying one. We have established an expression for the inductor before, which is VL equal to L times di over dt. So the electromotive force or the voltage across the inductor is given as the inductance times that varying current with respect to time. And over here we have established an expression for the current and the electrical circuit to be as I of t equal to V0 over R into 1 minus exponential minus R over L times t. So what we are going to do over here is we are going to derive the expression of that current with respect to time and then plug it over here in order to determine the expression for the voltage across the inductor. So di over dt would be equal to d over dt of V0 over R into 1 minus exponential minus R over L times t. And then we are going to expand that equation before we derive it. So d over dt is equal to V0 over R minus V0 over R times exponential minus R over L times t. Now starting with the first term, over here that first term it doesn't include any term related to time, therefore deriving it with respect to time is going to yield 0. Therefore let's derive the second term. And over here we are going to derive the exponential. T over here is to power 1, so dt over dt is going to yield 1. However, we have the term minus R over L, which is multiplied by t, therefore we take it out of that exponential. So we are left with minus R over L, which has been taken out of that exponential, times minus V0 over R over here, times exponential minus R over L times t. Therefore, di over dt is equal to R and R, they cancel, minus times minus is plus, therefore it's V0 over L times exponential minus R over L times t. Then we take that expression and we plug it over here. Therefore, the voltage across the inductor is given as L times V0 over L times exponential minus R over L times t, which is equal to finally VL of t equal to V0 times exponential minus R over L times t. And that would be the final equation for the change or the decay in that case, a change of the voltage across the inductor. So now after establishing an expression for the voltage across the inductor and that across the resistor and an expression for the electrical current in the RL circuit, now we are going to be representing graphically these responses, these exponential responses. So starting with the case of the electrical current. The electrical current, as we have seen before, it actually starts at I equal to 0 and then it starts to increment slowly and exponentially. So over here we have several time constants. After 5 tau, the electrical current in the RL circuit should reach its maximum value and stabilize. So initially it is actually starting at I equal to 0 and then it starts to increment slowly until it reaches its maximum value after 5 tau, and over here at 1 tau we have a certain increase of 0.63 of I0 or of I max, and over here I would be equal, or let's call it I would be equal to I0 or I max, meaning that we have reached the maximum value for the electrical current after 5 tau. Now regarding the voltage response across the resistor. Now across the resistor, the voltage initially started at 0. Since the current was 0, therefore the voltage was 0. So in a similar manner, also we have an exponentially increasing response which reaches its maximum value after 5 tau. Over here we have VR equal to 0, and over here after 1 tau we have a certain increment of 0.63 V0. Now regarding the voltage response across the inductor. Now across the inductor, the voltage over here, it started at Vmax. So VL across the inductor, it was V0 when it initially started. However, as time was passing by, the voltage across the inductor, it was decaying. So over here we have a decaying response across the inductor, and after 5 tau, that voltage, it reaches 0. And over here we have a certain drop of 0.37 V0 after 1 tau across the inductor. Now let's say we want to determine the percentage of the voltage drop across the inductor after t equal to 2 tau and the percentage of the voltage rise across the resistor after t equal to 2 tau. So we know that VL is equal to V0 times exponential minus R over L times t, which can be written as VL of t equal to V0 times exponential minus t over tau. So after t equal to 2 tau, therefore what would be VL? So in that case, VL is equal to V0 times exponential minus 2 tau over tau. Tau and tau, they cancel. On the calculator you find the value for exponential minus 2. Therefore you find a certain value. That value which is multiplied by V0 would represent the percentage. So, but in that case it would be the percentage by which the voltage across the inductor it had already dropped. Now regarding the voltage rise across the resistor. Across the resistor, VR is given as V0 into 1 minus exponential minus t over tau. So in a similar manner over here you replace t by 2 tau. So tau and tau they cancel. On the calculator you find the value for the exponential of minus 2. You add to it 1 and therefore you find a certain percentage for the voltage increase across the resistor. Now let's say you want to find the time it takes the inductor to discharge by 60%. So VL now is equal to 0.6 V0. Therefore, by going back to the equation of the voltage across the inductor, you replace VL over here by 0.6 V0, which is equal to V0 times exponential minus t over tau. V0 and V0 they cancel. And then you take the ln of both sides over here. Therefore we have ln of 6 over 10 equal to ln of exponential minus t over tau. Therefore we are left with minus t over tau equal to ln of 6 over 10. Therefore t is equal to minus tau times ln of 6 over 10. In case you obtain the negative value, you take the absolute value. So let's say over here tau, you already have tau which is L over R, or you find tau theoretically, or you already find it experimentally. If you have several values for it, you find the average and so on, and you use the average value over here. You plug it in that equation and you get the time it takes the voltage across the inductor to drop to 60% of its maximum value. And the same methodology would be followed if the same question was being asked for the voltage across the resistor or for the increase in the electrical current in that RL circuit. Now regarding the experiment it actually consists of two parts. In the first part you are finding the time constant for an inductor when it had free space as a central core, and in the second part you are finding that same time constant tau but for an inductor which has now an iron core as a central core. The difference is when you have an iron core placed as a central core, therefore an iron core is actually minimizing any loss of magnetic flux to free space. So when you have an increase in magnetic flux in the case when you have an iron core, therefore tau, which is equal to L over R, and tau over here it depends on the inductance. We have seen that the inductance is given as N times phi B over I. So the inductance is directly proportional to the magnetic flux. So when you have an iron core, that iron core is minimizing any loss of magnetic flux. So over here we are increasing the magnetic flux of that inductor. Therefore that inductance is going to increase, and as a result of that the time constant tau is going to increase as well. So whenever we have an iron core placed as a central core for the inductor, we are going to have an increase in the time constant and as well an increase in the inductance of that inductor. Whereas when we have free space as central core, free space is not a good conductor for the magnetic field. Therefore we are going to have some loss in that magnetic flux over here. So L is going to decrease, and as a result of that over here the time constant is going to be less. And that would be it for the RL circuit.